Hello everyone, welcome to a brand new video. In this video, we are going to talk about global descriptor table and how we can implement that. In the previous video, we wrote small portion of bootloader and we saw how how segmentation work and how segmentation is used to access the memory. So the trick was multiply the value inside segment register by 16 and add the offset, right? But the downside of that was the code part can basically access any part of the memory. So we need some kind of protection. So for that, we will jump to protected mode, that is 32-bit mode for that. But before going to protected mode, we need to implement global descriptor table in real mode and then enable the protected mode flag in the CR0 control register. So we will see how we can implement the global descriptor table in today's video. So first of all, let me explain what global descriptor table is in simple terms so that you can get a basic understanding of what it is. So global descriptor table is a table it is a array of entries, each of 8 8 byte long. So the first entry will always be null, and after the entry afterwards, we will basically define it how we want to build it. So I have built a notes for global descriptor table so that I can explain it to you with easiness. So for building these notes, I have used these resources. Okay, this is a good, like very good website that you should actually into it so that you can understand what is going behind the scenes. And I have used this resource a lot for making my notes and also for a lot of other things. And this is a good diagram that I got so that I can tell you what global descriptor table actually looks like. So the first 8 byte is, I told you, it's null descriptor, and then the later descriptor we will define it, and we will eventually first define it and then put it into a GDTR register where it tells the base of the global descriptor table and the limit, like how big the global descriptor table is, and then we will load it into the memory. So that is the plan. And also I will cover this is like an example of how the protected mode global descriptor table, how we will use that. So we will also cover that, but not whole, but some things that are really actually important to understand before we move to protected mode. So let's start the explanation. So as I have told you, the global descriptor table is a table of descriptor. Each descriptor is 64-bit long or 8 byte wide. It tells CPU where a memory segment starts, how big it is, how what permission it has, like if it is only readable, if it is writable, or it is only executable, and what mode it operates in. So this is the simple format that I made for the simple understanding. So this first 8 byte will be null, and then later we will write it into the descriptor table. So also one thing to understand is that before, in real mode, the segment register was used directly. Like we used to multiply the content of segment register value into 16 plus add an offset, right? But here segment register is used as a pointer, you can say. Like it used as a pointer to the descriptor table index. Like we will get the value from it, and which will eventually point to a index global descriptor table, and then we will analyze the table. So it is called 32-bit also. This is about 32-bit protected mode. It is called 32-bit protected mode because you can see, like each time we try to access some part of instruction of memory, the CPU will check the boundary. Like also it will use the global descriptor table to say to see the limits, what privilege it has got, like if the valid segment is in the memory or not. So that's why it adds a new layer of protection to the memory. So this is the diagram that I made to understand the each entry. So it will contain a base, a limit, access byte, and flags. The access byte and the flags are the two really important thing that describes the segment in the memory. So later in the video, we will go much deeper into access byte and flags. So but for now, let's just understand the limits and the base. So limit is a 20-bit wide value that represents like how big the segment is. Okay, there will also be a thing called granularity, which will say like if the limit is in bytes or in pages, in 4 kilobyte of pages, but we will cover that in later video. And for the base, it is 32-bit value. That means it can represent from 0 to 4 gigabytes of value. But for the flat memory model, we will use a limit equals to the maximum value that we can represent from 20-bit, and for the base we will use 0 because we are using a flat memory model. Uh, so limit it here we have 16 bits, and here it covers 4 bits, that means totaling 20 bits. For base, we have 16-bit over here, and 6 and 8 by 8 bits over here, and where is another uh oh sorry, for the I was talking about base, right? Oh yeah, for base the 16 is over here, and the 8 is over here, and the 8 is over here, so totaling 32-bit value. So now let's look at the access byte. Okay, so the most significant bit, that is the bit 7, is the present bit. Like this is the first thing that the CPU checks to identify if a segment is valid and it is in the memory or not. Okay, so if it is 1, that means the segment is in the memory, and if it is 0, that means there is no segment in the memory. So for the bit 6 and 5, it describes the descriptor previous level. So we have a previous level thing, that means the 0. So we use 2 bits, right? So 2 bits can represent 4 values. That means we have 4 rings in terms of the previous level, and the 0 representing the highest privilege level, that is of kernel, and the bit and the value 1 and 2 is basically given to the device drivers, and the last value, the 1 or 3, is given to the user application, and it also represents the lowest privilege level that anything can have. Okay, and the bit 4. So bit 4 is a descriptor type bit. That means if it is 0, it defines a system segment. I'm not going to deep dive into what system segment is. You can look into the notes that I have provided, like the website that I told. It will also be in the description, so you can look into it. But for now, we will only look into bit 4 equals to being a 1. That means it defining a valid code or a data segment. So so let's say if the bit 4 equals to 1, that means it if it defines code or a data segment. So the bit 3 will define if it is a data or code segment. Like if the bit 4 equals to 1, it represents code or data segment, right? But we don't know what particular, like if it is exact code or if it is data. But the bit for that purpose, bit 3 is used. Like I have written it, if bit 4 equals to 1, then if bit 3 equals to 0, then it is a data segment, and if it is 1, then it is a code segment, right? So now let's jump into bit 2, that is for like directional or confirming bit. Like same thing here, same idea here. So if bit 3 equals to data, that means it can be it can grow upward or it can grow downward. Like if it is 0, it grows upward. That means if it is used for global variables, heap, array, matrix, etc. And if it is 1, and it grows downward. So bit 2 is called directional bit if it is a data, right? And if it is 1, then it grows downward and it is used for stack. But what if it is for the code? That means bit 2 is confirming bit. So what basically confirming bit is mean? Like if the confirming bit is set, that means less privilege, any user application or anything that has lower privilege level also can execute this privilege level that we have. That means, let me explain it more clearly to you. So if it is zero, this code segment can only be executed with ring privilege equals to descriptor privilege level. That means the privilege level that anyone will be executing that segment will have to be equal to the descriptor privilege level. But if it is one, anyone that has that has lower privilege level than the uh, descriptor privilege level can execute that code. I hope you understand it. I also have a table, so it is easier for you to understand. So if, let's say, if the descriptor privilege level is zero and the confirming bit is one, that means anyone from the caller that has privilege level 0, 1, 2, 3 can execute that valid segment. And if the descriptor privilege level is 1, then 1, 2, and 3 can execute it. So I think you got what I'm trying to say, right? So that is for the bit 2, like directional or confirming bit. So now let's look at bit 1. So also, if bit 3 is equals to 1, so it tells us that it is a code segment, right? So what bit 1 tells is that if bit 1 equals to 0, the code segment is not readable. And if the bit 1 equals to 1, saying that bit 3 equals to 1, uh, the code segment is readable. And also, one also important thing is we are never allowed it to write into the code. That is, write access is never allowed it for the code segment. So let's see if the bit 3 is 0, like if we are talking about data segment. If we are talking about data segment, then if bit 1 equals to 0, that means we don't have any write access to that data segment. And if bit 1 equals to 1, that means we have write access. And also same applies to the data segment. Read access is always allowed it to the data segment. Like it is also like opposite, what I'm trying to say. And bit 0 finally is the access byte. That means if it is equals to a equals to 0, that means the segment has already been used. But oh, sorry, if it is equals to 1, the segment has already been used once, at least once. And if it is 0, that means the segment has not been used. So that is for the access byte. Now let's look into the flags. So the flags is really simple, okay? So we have four bits that represents the flags. The bit 0 is reserved. That means it is used for software, like operating system uses it. So let's jump into bit 1. So bit 1 represents the long bit mode. That means if it is 0, it says like it is not a long mode. So it can be 16 or 31, which is controlled by the DV bit. Okay, so if it is 1, then it indicates long mode. That means we can ignore DV. But the convention is that if L equals to 1, it says that it is a long mode, right? So DV must be 0. Like if L equals to 1 and DV also equals to 1, and the CPU will throw some kind of exception and it won't happen. So that is the case. So let's see, if L equals to 0, it says like it is not a not long mode, right? So we need to understand like if it is a 32-bit mode or a 16-bit mode. So if D equals to 0, it is a 16-bit code. That means everything like 60, we have 16-bit instruction, 16-bit offset, 16-bit code. And if D equals to 1, we have 32-bit code, 32-bit instruction, 32-bit offset, and 32-bit code. So I also have a table for this. Like if L equals to 0, it is saying like it is not a long mode, it is not a 64-bit mode. So DB equals to 0 means it is 16-bit. So you can look into the table. So also if L equals to 0, L equals to 1, DB has to be 0. If it is 1, then it is invalid. Okay, that is the thing. So the three, let's look into the bit 3, that is for the granularity, sorry for the pronunciation, granularity bit. Like it describes the limit. So like if the limits that we have, we should take it in bytes. or in kilobytes, like in 4 kilobytes. So if g equals to 0, segment is in 1 kilobytes, one byte, sorry. And if g equals to 1, segment is in 4 kilobytes. So that means if when g equals to 0, segment can be from 1 byte to 1 MB. Like it is really less, like, right? And if g equals to 1, segment is from 4 kilobytes to 4 gigabytes in length. Like that is all the address space in 4 GB of memory space, right? So also I have wrote it like for this we will the limit is shifted 12 bits to left. Like that means we multiply it by 4 gigabytes. So to convert it, this is a conversions thing that you need to understand if you are implementing it, but don't worry about it. So the last thing we need to understand before we code in next video to understand is segment selector. So selector is nothing but the value in the segment register. So it is loaded in the segment register. So it is a 16-bit value, and what each field represent is like the 2-bit is used for the ring privilege level. That is the sorry, ring, not ring, requested privilege level. So I have already explained is like 00 is the highest and 11, that means the ring 3 is the lowest. So access is only granted if the value is lower, like if the requested privilege level is higher than the segment that we are talking about. And the bit 2 is the table index. If the table index equals to 0, that means we are looking at global descriptor table. And if the table index equals to 1, we are looking at local descriptor table. And the rest, that is 30-bit. And if you know 2 to the power of 13 is 8192. So we total can have 8192 descriptor. So that is it. And for our global descriptor table, the ring privilege level will be 0 because bootloader has a kernel level privilege. And for the table index, it will be 0 because we are looking at global descriptor table. So that means bit 2 to bit 0 is 000. So that is all you need to understand about global descriptor table. We will implement the global descriptor table in the next video. I have just made an explanation video in this video so that it is easy for you to understand what we will be doing in the next video. But before we go, I want to explain this thing, okay? So what I'm telling it is, suppose we need to access some kind of memory, let's say, okay? So first of all, what will happen is we have an offset, right? We will always have an offset because we're trying to access some memory. So uh, suppose the data segment is 0008, then this will eventually point to a entry in the global descriptor table. So this 000, this is a content in the descriptor table, and here we have access byte flag, and the CPU will check everything. So if it is valid, then it will extract the base from here and add offset to it, and eventually we will access the memory. So you understand how it adds a layer of protection. Like if the global descriptor table says that we don't have any privilege to get into that memory, or say if we don't have any valid segment, then we won't be able to access the memory. That's how we have an extra layer of protection that we are talking about. Also, I hope you guys also look into this website, because this website is also very important. And if you want to understand the real thing behind bootloader and everything, so I hope you guys are doing good. And let's see, I will see you guys in the next video. Thank you for watching.